Okay, next up, we're going to now put these AI methods into action. A very special guest who's been a part of the project for most of his professional career. Mathias started, I think he may have been the very first intern on the Living Heart project early on in his career. He's now assistant professor at University of Delft University, doing amazing work, and he's going to share his research on physics-based modeling and how AI can really accentuate the performance and speed, some things we've been talking about earlier. So let me invite, please join me in welcoming Mathias to the stage.
All right. Hi, everyone. My name is Mathias Peirlinck. Today, I want to give you some insights into some machine learning techniques that we have been using over the last couple of years and how they have helped us find some, or like how we have used them synergetically with physics-based modeling to come to some insights into human heart physiology and pathophysiology. So I don't need to convince this audience about the power of physics-based modeling, how we can use multiscale, multiphysics framework to explore human heart electrophysiology, mechanics, and fluid dynamics, for example, both in healthy and diseased populations. I think this whole meeting is a nice testament of how we can use this for medical device innovation, personalized treatment strategies, regulatory verification, and this improved understanding of cardiac pathophysiology. And this is a quick link still to the review paper we wrote with part of the consortium 2 years ago. However, what I wanted to focus on today is that we can only build those models if we have a thorough understanding of the physics. And that typically comes from a lot of data. So it's no surprise that we have a healthy living human heart model that's an average. But in the case that you have a very specific population, you don't always have all the physical knowledge available. And then typically in our field, I would say we are somewhere on this spectrum that you can see here. So on the left, if we have a lot of understanding, we have translated that understanding to physical laws, and we can use multiscale modeling with only a limited amount of data to inform us about what the human heart, how it functions, basically. On the other hand, if we would have from a specific patient a lot of data, or like of a lot of patients, basically, we can just use machine learning because of its powering correlation. However, in our field, we're typically somewhere in the middle. We have some data and we have some physics. And so what I want to talk about to you today is like how can we efficiently deal with some data and some physics? And so how can we combine multiphysics modeling with machine learning in an efficient way? We can use, for example, multiphysics modeling because of its strength in bridging the scales, in mechanistic regularization, causal extrapolation, and data augmentation on one hand, and then use machine learning for other aspects such as uncertainty quantification and propagation, multi-fidelity modeling, model discovery, as was alluded to before, or like explained before, surrogate modeling, and data-driven interpolation. And so what I want to talk about is this synergy. How can we leverage them? And I'm going to do that with 2 case studies of 2 papers we have published in the last couple of years. And I'm going to focus on these techniques more specifically. So the first paper was back from 2019, and we were looking at cardiac growth and remodeling. So we wanted to understand how the heart's function, how the mechanics is changing over time. And so we do that with multiscale cardiac growth models. And what those are, in a nutshell, is that if there's an event at the organ scale, for example, a leaky valve or like a pressure overload, what happens is that mechanical environment changes. That's felt all across the scales. And at the subcellular scales, typically you have a response. There's remodeling processes that then can be felt all the way up to the organ scale again. And that's a process that keeps on continuing over time. And the way that we typically do this is by using the kinematic-based growth framework, for example, where you define how the growth is changing due to changing mechanical stimuli, for example. However, an important aspect of this framework is FG. That's the growth deformation tensor. And very often that's, if you look at the literature, there's a lot of uncertainty on which growth law is now actually correct, like which one this explains the behavior of cardiac tissue correctly. And that's also mostly because of a lot of uncertainty in the data that you need to quantify or at least validate one of these growth laws. And so in this study, we actually wanted to quantify the predictive capacity of such a growth law, which was not really properly done yet until that point. And so what we did is that we had access to animal data. So there was like an animal trial with 6 pigs where systolic heart failure was induced by mitral valve regurgitation by cutting the chordae. And we studied the organ and cell scale changes. And what we wanted to do is use the experiments on one hand, but also have computer models on the other hand and see how well they overlapped based on a specific growth law. And so there's some challenges in doing that, and that's why also this wasn't done yet into all that detail yet. First and foremost, experiments are notorious for noise, for uncertainty in the experimental data, and so we had to deal with this. And we used 2 techniques, Bayesian inference and hierarchical modeling, most specifically for uncertainty quantification here. So what is Bayesian inference? As I said, I'm going to give you some insights into some of these techniques. So Bayesian inference is based on Bayes' theorem, which describes the probability of a hypothesis or a parameter set theta, if you will, based on prior knowledge and observed evidence. And that's boiled down into this, this formula that you can see here, which has 4 terms. The most important term, or the one that we're after, is the posterior distribution in blue, and that's the probability of your hypothesis or your parameter set theta given the evidence X, so the data that you have collected. And that's what we want to learn, basically. The other terms are the prior distribution, so that gives you the opportunity to put some initial beliefs or knowledge that you have on a certain problem within your framework. You have the likelihood that actually couples this together, so that's the probability of your data X arising from your parameter set that you're assuming, and then you have the evidence, which is the denominator there. And so we're looking for this one, and there's, depending on which distributions you have in your problem, there's multiple ways of doing this. Very often we cannot use analytical solutions, and then we often use the Markov chain Monte Carlo. I have other slides on that, but that can be discussed in the break for time concerns. And then I mentioned Bayesian inference, but we combined this with hierarchical modeling. And why hierarchical modeling? Well, hierarchical modeling actually allows us to make the most of the data that we have, because a lot of the data that we are collecting can be thought of in a hierarchical sense, or it is actually hierarchical in its structure. And a very simplistic example of this is like, for example, take that you have a genetic condition that is affecting certain subjects, and you have, for example, tissue experiments that you do on those subjects because that condition is known to affect the stiffness of the tissue, for example. So there's 2 extremes in how you can then fit parameters to this. So one is where you're throwing all the data together in one whole group model, and then you're actually underfitting because you're taking out all the richness of the data. On the other hand, you can basically fit parameters to each specific experiment, and you're overfitting, and you don't really have an idea of what the whole population is doing. And so hierarchical modeling sits somewhere in the middle there because it allows you to give you one set of parameters per subject, per sample, but you still take the whole population into account. And so in this example, what that means is we put the hierarchy of the data into the way that we are quantifying the uncertainty. So you have all the samples per subject, they are part of a hyperdistribution of the condition, and then you can start using that to compare different conditions relative to each other. And what this allows you to do is to reduce the lower level parameter sensitivity to noise, and also identify the variability within and between subjects and populations. So back to our example, so how did we use this? So for the experiments, for example, in these pigs, every 2 weeks we had histology measurements, and we wanted to learn how the cell scale changes were changing, or how the cells were changing over time. So we had myocyte length and myocyte width, and this is the classic example, this is the classic problem. What can we learn from this data? There's so much noise in there, it's very hard to find patterns. And so we used hierarchical modeling to structure the prior distributions that are very uninformative. And then we put the data on top of this. So you have the experiments, you have the subjects, the pigs, and then the whole cohort. And doing this, we can actually quantify uncertainty, not only of the cases where we had a lot of data, but we can also use this for the cases where we didn't have a lot of data. For example, pig number 3 and pig number 5, we only had a certain weeks, but we can still accurately learn something about the uncertainty that we expect from the other time points. And then secondly, we were doing the computer models, and what is important to have there as well is that you want to propagate the uncertainty that you have in your experimental data. And here we use surrogate modeling, not neural networks, as was explained this morning, but we used Gaussian process regression to do this. And so what was our problem? So we have this certain hypothesis that we wanted to test. And so the normal way of doing that is just having deterministic models where you're predicting how a volume overload leads to cell myocyte lengthening. But we had also uncertainty in the input. So we had uncertainty in the volume overload. And there's then two ways to do this. You can sample for each of these pigs, do 1,000 simulations each, but that's computationally not super attractive. So we used Gaussian processes, and Gaussian processes are a technique to surrogate your model where you also still take the uncertainty into account of making such a prediction, which is a little bit different from a neural network approach, I would say. So you learn a function y is fx plus epsilon, which is the uncertainty that you have. And you can think of a Gaussian process as a probability distribution over possible functions that fit a set of points. So you have a very general distribution, and then you're conditioning that on your observations so that you can actually, and you do that with Bayesian inference so that you can actually also still have uncertainty in the regions that you haven't really sampled yet. And so we did this for this study, allowing us to, so what we did is we took the uncertainty of the input, we trained this Gaussian process regression, we tested it, made sure it was performing accurately, and then we used that to propagate the uncertainty through our models. And this was actually the first time that someone really quantified with uncertainty taken into account how such a predictive law was working on cardiac tissue. Then taking a step back to the second study, this was a more recent study where we also used these synergies, and this is focused on sex differences in drug-induced arrhythmogenesis. So as most of you know, drugs are notorious for affecting the heart in different ways, and dofetilide is one of these drugs that is notorious for causing early after depolarizations at the cell scale, which can then, at the organ scale, in a multiscale multiphysics framework, lead to severe consequences such as torsade de pointes, for example, which you can see here. And we coupled this also to the mechanics and the cardiovascular circulation in a recent paper. However, what we wanted to use the models for here is to know the sensitivity to drug-induced ion channel blocking, because they can bind to each ion channel basically on the cardiomyocyte. And then the question is, what combination is risky? Doing that in the full multiscale models is computationally intractable because those simulations just take multiple hours on multiple CPUs. So it wouldn't be possible to just explore this whole parameter space easily. So we did this in two stages. First stage, we just did cell scale simulations and looked at looked with logistic regression and marginal effects for the most important ion channels that can lead to drug-induced arrhythmogenesis. And then we focused on those two, and we set up this parameter space that you can see here. Beta KR is the one ion channel blocking, and the other one is CAL. And so within that parameter space, you can have different combinations, which for different drugs will be somewhere in this space. And so a naive approach would be to just try to fill this completely and have risky or unrisky results, and then use that to find the classification boundary. But again, computational cost would not allow us to do this. So instead, we used multi-fidelity Gaussian process classification and active learning. Another term that I need to explain to you is multi-fidelity modeling. So what do I mean with multi-fidelity modeling? Well, we all know our multi-scale high-fidelity models. We all love them because they're accurate, but the problem is that they're costly. And so what is the problem with that? If we want to speed them up, if we want to do a Gaussian process regression, for example, we still need quite some samples to train these models, which still is computationally inhibitive. So to fill, to limit down the uncertainty between those points, we still need a lot of simulations. So the question with multi-fidelity modeling is well, what can we do with the lower scale simulations, like the low fidelity models? They are cheaper, they're less accurate, but they're cheaper. So there it's way easier to sample more points. And then the idea for multi-fidelity modeling is, can we use those low fidelity results to still help us in the high fidelity space? And actually, we can do this. So the way that we do that is that we first train a Gaussian process basically on the low fidelity simulation space, and then we learn the bias or like the error between the low fidelity models and the high fidelity models with another Gaussian process. And what this does is it allows you to, for example, here if you have no low fidelity simulations but just 5 high fidelity simulations, you have a lot of uncertainty. But without doing extra high fidelity simulations, you can still shrink down the uncertainty that you have in your high fidelity space, as you can see here in a very simplistic example. But we use this for sex-specific drug sensitivity study here. So how that worked is that we first did cell scale simulations. We filled the parameter space with Latin hypercube sampling, trained a Gaussian process to have a first rough idea of where this classification lies in the low fidelity space, use active learning to really explore and exploit that boundary. And then in a second stage, we add these round circles, which are the high fidelity simulations, and we learn the bias between low fidelity and high fidelity simulations so that you can see how this boundary actually shifts for this specific case. And so by doing that, we were able to train an arithmogenic risk classifier for both men and women, which were different, and we used also multiscale modeling here to look at the sex differences more specifically. So in conclusion, I hope I shared with you how we can use physics-based modeling and machine learning to have important opportunities for uncertainty quantification, for uncertainty propagation, sensitivity analysis, and hypothesis testing. And just to show you how useful this is, we have not only used this for heart modeling, we have also successfully translated this to modeling the propagation in Alzheimer's disease, and even COVID outbreak dynamics, where we had tons of data, but also with tons of uncertainty. And it's important to take that uncertainty into account here. And so with that, I want to finish up with a little extra that I worked on the flight over here. If you want to have your living human heart on your phone, you can easily now use an augmented reality model that I created of the simulations. So feel free to play around with the heart as well. Thank you.
Fantastic. Great job.
Thanks.
Okay. We have time for a couple of questions for Mathias, if we have. Any from the audience? So I actually have, well, I have many questions, but there's always a question when you have these higher order or lower fidelity models, how do you know where it is on the curve of fidelity? One of the reasons we like the high fidelity model because it's just trusted, right? Mm-hmm. So there's a kind of a continuum, if you will, once you leave that. Yeah. How do we classify these higher order models, do you think? Is there a way where we could bring some consistency to that?
Well, I think with like the kinds of approaches that we have explored in the past, it's very interesting to quantify the uncertainty on your predictions in the different fidelity spaces. Mm-hmm. And that can allow you to learn whether or not a low fidelity modeling mm-hmm. approach is actually still helping us or not. Because if the bias cannot be easily learned, then you might have a way to consistently look at like whether or not that's too low fidelity, I would say. But in this case, it worked perfectly, actually. So it was very useful for us to bring those into account.
Okay, so basically spot test and you'll know.
Yeah.
Fantastic. Okay. Well, I certainly, Mathias was very generous in covering a lot of material in a short period of time to help us stay on schedule. There's an immense amount of detail behind that. I think you'll find incredibly useful. So follow up with him, look at his publications. Fantastic work that I think you'll learn a lot about. Do we have a question?
Sure, I have a question.
Oh, great.
Do we have time?
Yeah, go ahead.
Okay, so like I think this is kind of related to your question, but like, so when I think of low fidelity versus high fidelity, I think of mesh convergence studies. So so I'm wondering, I myself thought, oh, I can use a lower fidelity mesh and it'll run faster, but then you have to consider the mesh that it hasn't converged. The mesh hasn't.
No, there's usability in that as well for this. So you can indeed like have a very fine mesh and still have like faster models that are your lower fidelity space as well. So that's definitely also an approach you can do with this. And I think Francisco, together with Adrian, did this as well for skin modeling.
I was misunderstanding. I thought lower fidelity meant a coarser mesh, but that's wrong.
Not necessarily. In our case, that didn't mean it. For us, that was just like we only have the cell scale model, which is just one set of ODEs. And then in the high fidelity, we had also the PDE, so it like describes how the electrical signal is traveling through the heart. But we showed that we can still learn the difference between those two with a multi-fidelity approach.
Yeah, very powerful combining them.
Yeah.
Very impressive takeaway. Okay, please, once again, thank Mathias.